everybody. We are entering the series of lectures that are going to go over the EKG. Now, those of you that have exercise phys undergrad majors have taken a class in EKG, and those of you who are not, this is usually a pretty new introduction. So, if we are in class in the normal world, I would give students the options of coming to this lecture or not, because for everybody to understand EKG, we have to start at the very beginning, and we really have to go through the basics of EKG. So if you are somebody who feels really solid in this content, you could skip the introductory video and go right into the discussion of rate and rhythm disturbances. If you'd like the refresher, please feel free to watch. For those of you who have never been given any EKG content, we're starting from the beginning with this video so that you're introduced to it at a pace that allows you to fully understand what we are recording and what information we can get from the EKG. So I'm going to start with the introduction here, and I will begin the next video series once we get past the basic introductory concepts. So the first thing we have to remind ourselves about and discuss is the way action potentials are generated in the different cells within the heart. So our myocytes are the muscle cells of our heart, and they're represented on my picture here in red. In your notes, it's the one on the left. And cardiac myocytes have a resting membrane potential of around -90. They sit at about -90 millivolts. The reason they have this negative number is there is a constant outward flow of potassium ions that leak out of the myocytes, and that helps keep them in that negative place. The reason a myocyte develops an action potential is because a neighboring cell, whether it's a myocyte or a pacemaker cell, has an action potential. If you remember, the cells in our heart are what we call a functional succinction. There's gap junctions between the membranes. So if a neighboring cell has an action potential, it will cause the next cell over to it to start having a more positive resting membrane potential. And in fact, sodium ions will leak in. When the myocyte hits -70 millivolts, this is the threshold for opening of the fast sodium channels. So in your picture on your notes, this big first spike is labeled as a 1. And the 1 is when you reach the threshold to open fast sodium channels and positive sodium ions rush into the cell. It's going to very, very quickly change the resting membrane potential to become very positive. But just as soon as those sodium channels open, they close again. These are voltage-gated channels. So when they hit a threshold potential of -70, they open, and as soon as they get past 0 millivolts, those fast channels begin to close. But unlike a neuron, which has an action potential that's driven in a very similar fashion, voltage-gated sodium channels allow this spike of positive change in membrane potential. Unlike a nerve, myocytes have a second channel, and those are L-type calcium channels. L-type calcium channels open as soon as the membrane potential gets above -40 millivolts. Now, these L-type calcium channels have a much slower influx of calcium. So instead of having that spike like a neuron that spikes and then goes away, kind of labeled 2 in your notes is this plateau that happens in the myocyte. The slow influx of calcium creates an electrically balanced situation that kind of just holds steady the membrane potential in this positive place. At this point, Potassium is beginning to leak out, but calcium is coming in, and so we're staying in this balanced place. Eventually, the calcium channels close, and that is when number 3 on your note packet, this is when repolarization happens. When the calcium channels close and there's no longer an influx of calcium into the cell and potassium is still moving out, you return back to the resting membrane potential. So this is what an action potential looks like in a myocyte. And the plateau is a really important element because it helps protect that cell from having another action potential too quickly. So that plateau kind of guarantees that our heart does not go into kind of a tetanus situation. On the right is the action potential of the sinoatrial node, the SA node. The SA node is a very important part of the heart because, as you guys probably already know, this is where we control our heart rate. And what's interesting about the SA node is it does not have the fast sodium channels. So there are no fast sodium channels in the SA node. So the response of getting an action potential in SA node is actually much slower. If you kind of look at the slope of the line here, there's kind of a slower response than you compared to the straight vertical line of the myocyte. What's really special about the SA node is that it has leaky sodium channels. The leaky sodium channels allow the membrane to let sodium come in, just kind of slowly leaking in, which was going to slowly raise the membrane potential. Because the SA node has these leaky sodium channels and sodium can just leak into the cell, the SA node can spontaneously depolarize. This spontaneous depolarization opens up calcium channels. So with the change in voltage caused by the leakiness of these sodium channels, we can open calcium channels, allowing calcium to rush in, which is where we get the further depolarization. Eventually, calcium channels open, which allows you to repolarize back to baseline. This is kind of a textbook image of the same idea that just draws that contrast between the myocytes here on the right and the SA node on the left. You can see that the slow drift towards threshold that happens in the SA node is related to the leakiness of the sodium channel. But once you reach threshold, that's what opens the blue calcium channels, and now calcium rushes into the cell, creating a positive change in the membrane potential. As potassium starts to leak out of the cell, it repolarizes it back to its resting membrane potential, and then it will start leaking again. And then we repeat, and around and around and around we go. Which is different from the myocyte on the right, which the resting membrane potential is basically maintained by this outward leak of potassium. And then in response to a neighboring action potential, you get this rush of sodium into the cell. The big difference between a myocyte and a nerve is that in both situations, in the nerve and the myocyte, the fast-acting sodium channels close very rapidly. But unlike a nerve, this plateau phase is related to calcium channels, which are not there in the nerve. So it holds you in this plateau where you stay in a positive membrane potential longer, protecting that cell from having another action potential. But eventually the calcium channels do close, and the repolarization is due again to that outward leak of potassium. So this is a textbook image of the electrical kind of circuitry of the heart. So we've been talking about the action potential in the SA node, which sits up in the right posterior wall of the right atrium. It's literally kind of just below the superior vena cava. The SA node, as you guys know, is the rate controller of the heart. What I'm going to do is on the next page in your notes, you can see a sketch of this heart. We're going to take some time and actually really draw out these electrical circuits because this is probably one of the most important introductory concepts. If you understand the details of how the electrical current moves through the heart, all of the rhythm disturbances will make sense when you go back to these basic concepts. So this is a really important area to draw this well, take some good notes, because when we start talking about when things go wrong, it'll make a lot more sense if you know what was supposed to happen when things went right. So let's first draw in our SA node. So if you can follow my picture, this is the right atrium that has, I'm just going to draw this a little more exciting because it has such a big job to do. Green for SA node. So I'm going to erase this in a second. Don't draw along with me. But here we have right atria, right, leading into right ventricle. And this is left atria leading into left ventricle, just to orient you to my drawing. All right, the SA node, again, right, is in that posterior wall of the right atrium. We talked about the fact that the SA node can spontaneously depolarize, and it has an intrinsic rate. If you cut the SA node out and you put it in a dish and you watched how frequently it would have an action potential, it would have an action potential 70 to 80 times per minute. So the SA node, if not controlled by any other thing, would cause your heart to beat 70 to 80 beats per minute. So the SA node can spontaneously depolarize, and it will transfer that action potential to all of its neighbors. But it has these very specific routes that allow the action potential to travel very, very quickly, and those are called internodal pathways. These internodal pathways are in I think that's kind of blue. Internodal pathways. These are significant because they have 2 times faster conduction than a nodal cell, like a cell that's in the SA node or the AV node. So it allows for very rapid velocity of conduction. So internodal pathways have super fast conduction. So it spreads that signal throughout the atria really, really fast. Those are internodal pathways. Their benefit is they have very, very fast conduction rates. They end up coming together at a very specific point, which is the AV node. So we'll draw that here. In true purple is our AV node. So the AV node is in the posterior wall of the right atrium. It's literally just behind the tricuspid valve, and it has a very specific purpose. The AV node is designed so that the action potential that originates in the atria doesn't travel directly from the atria to the ventricle. In fact, at the AV node, we see a 0.12 second delay in the transmission of the action potential. This is related to both the AV node and then some of the penetrating fibers. For those of you who are a little more into the physiology nerdery of this, the reason the AV node is able to this delay is it has a decreased number of those gap junctions. Gap junctions, again, are the way in which the neighboring cells all kind of share the same ionic environment, because the gap junctions allow the insides of the 2 cells to kind of talk to each other. So in the AV node, if there are fewer gap junctions, it takes longer for the action potential to bounce from one cell to the next cell to the next cell. In fact, it takes about 0.12 seconds longer than other areas in the heart. So the AV node serves a very specific purpose of delaying the action potential. The reason you want to delay the action potential is because you don't want the atria and the ventricle contracting at the exact same time. You want the atria to contract first, so it does that surge of blood into the ventricle right before systole, and then the ventricle contracts right after. The AV node, the cells of the AV node, have their own intrinsic rhythm. If I cut the AV node out and I put it into a petri dish, it would cause spontaneous action potentials. This is an important one to write down. If the AV node is all by itself and nothing is influencing it, it would have an intrinsic rhythm of 40 to 60 beats per minute. 40 to 60 beats per minute is the intrinsic rhythm of the AV node. So if something isn't talking to the AV node, if there's some disconnect between the action potential getting through the atria to get to the AV node can take over and drive the rhythm of the heart. But then you'd expect the rhythm of the heart to be 40 to 60 beats per minute. So our action potential originates in the SA node simply because its intrinsic rhythm is the fastest of all the cells in the heart. The SA node has an action potential. That action potential spreads, and it spreads very rapidly through the atria because of internodal pathways. But when it hits the AV node, it slows it down just for a little bit. But once it gets all the way through the AV node, it has made its way to the ventricle. And then we have some very important fibers called the Purkinje fibers that are in red. Blank in here. Purkinje fibers. Purkinje fibers are significant because much like the internodal pathway, they have a very high rate of conduction. They conduct the action potential 150 times faster than the AV node. They're 6 times faster than an individual myocyte. Super, super fast. How do they do it? They have increased numbers of gap junctions at their intercalated discs. So the action potential spreads extremely rapidly because there's a whole bunch of holes in the wall that allow the ionic differences to spread from cell to cell extremely rapidly. So Purkinje fibers have the advantage of spreading that action potential incredibly quickly through the ventricle. The cells of the Purkinje fibers also have an intrinsic rate. They will have spontaneous action potentials all on their own if kind of removed from this system or not influenced by all these other neighboring cells. The Purkinje fiber's intrinsic rate is 20 to 40 beats per minute. If you cut the Purkinje fibers out and you put them in a dish, they would spontaneously action potential every 20 to 40 times per minute. I didn't write it on here, so I just want to make sure we're remembering the importance. I'm going to add it to my whiteboard, so as you see it, it is important. The conduction velocity is really the key here. All right, so this is the path that the action potentials take. So there's some important things to kind of put on here so we remember when we start talking about rhythm disturbances. The pacemaker of the heart is the SA node. If anywhere else in the heart is controlling the rate of the heart, so if something else takes over and is controlling the rate of the heart instead of the SA node, you call that an ectopic pacemaker. When the pacemaking of the heart is coming from anywhere other than the SA node. That's ectopic pacemaker. So we will talk about this happening where the rate of the heart is originating from a place that's not the SA node. And when you know the intrinsic rhythms of some of these different areas of the heart, it can help us figure out what area of the heart is controlling the rate. So that's the ectopic pacemaker. We kind of went through the importance of the AV node as that junction between the atria and the ventricle, that necessary path to spread the action potential from the atria to the ventricle. If there is something that fails in this area, that you might have had ischemic damage or some other reason that the cells stop working in the AV node, we call these are when we start talking about heart blocks. A heart block is when there's a disconnect between what's happening in the atria and what's happening in the ventricle. That's a heart block. And then one of the more common phenomenon that can happen is that you get what's called a ventricular escape rhythm. A ventricular escape rhythm is when the rhythm is actually coming from the cells within the ventricle, largely driven by those cells within the Purkinje fibers. And you can see this really low 20 to 40 beats per minute is a classic finding of the ventricular escape rhythm. So we're going to circle back to these when we actually talk about rhythm disturbances, but feeling very comfortable with how the action potential moves through the heart, the significance of these different spots of the heart. We've got two areas where we have nodal myocytes. We call them SA node and AV node. Our nodal myocytes are very electrically excitable, but in general have pretty slow conduction, where our internodal pathways and our Purkinje fibers, the benefit is they have these really high conduction velocities. So we've talked about how the individual myocytes and SA node generate an action potential. Then we drew out the path that action potential spreads throughout the heart. Now let's talk about how we record that action potential or that electrical activity of the heart with the EKG. So what's on your screen here is a cardiomyocyte. So you can see kind of a lot of these channels that we talked about. You have the sarcoplasmic reticulum in the center holding all of that calcium. You can see a T-tubule here, right? That same structure where the action potential can open up the channels to allow calcium to get released into the cell. And that calcium is really responsible for the contraction of the myocyte. When we're talking about recording this, here are those leaky potassium channels, right? We're leaking potassium out, and that keeps us at this like negative 90 millivolts. So we're very negative inside of the cell. So you can almost put like little negative signals all on the inside of this cell because the intracellular environment is very negative. And these potassium ions have leaked out, which means we're very positive on the outside, which this is how it is drawn in your notes here. So this is meant to be the cell. And you can see it's negative on the inside and positive on the outside. So we can actually record the electrical activity in the heart by measuring kind of when these charges change. So we can put little sticky pads on our skin, and what we actually attach to our skin is called an EKG electrode, right? The conductive pad attached to your skin. And we can use those to record an EKG lead. So an EKG lead is the graphical description of the electrical activity of the heart. So just to make sure those words are separate. The electrode's what you stick on your skin. The lead is the graphical description that you get from the recording of the electrical charge. Graphical description. So in your notes, you might want to draw this little kind of EKG recording device here. And notice it has a negative, a neutral, and a positive on the dial. And this electrode that comes out, the negative electrode, is called your reference electrode. And we call it the reference electrode, but in the EKG, this could actually be physically 2 to 3 electrodes. We'll get into that, but they would be categorized as the reference electrode. The other side, right, is our positive. Our positive is called the exploring electrode. And we get a reading, right? This graphical description, this EKG lead, is going to record the difference between these two measurement points. What's the difference between your reference electrode and your exploring electrode? And right now, they are both recording a positive potential, and so the dial is reading 0. There is no difference between your reference and your exploring electrode. Let's draw this out, and you have kind of 4 little tubes in the bottom to show the different phases of depolarization and repolarization. So at the beginning, a depolarization, the inside, right, has become positive because we've had an action potential, which means the negative is now outside. That action potential is spreading throughout the cells of the heart, right? It's taking that path that we just drew on. So at this point, our reference electrode is here, our exploring electrode is here. Our exploring electrode is positive in relation to our reference electrode, which is now negative. So our lead is going to have a positive deflection, the graphical representation of depolarization. It's going to be in the positive direction because our exploring electrode is positive when compared to the reference electrode, which is negative. When the entire piece of the heart, the whole depolarization goes through and every cell is depolarized, well, then it's positive all throughout. The whole inside of the cell is positive. The whole outside is negative. So now the exploring electrode is the same as the reference electrode. So your graph goes back to 0. You go back to the isoelectric line because there is no difference between the reference and the exploring electrode. There's a lot going on electrically within the heart, but remember our recording that we see on the EKG is only letting us know what's the difference between these two electrodes. Okay? When a heart is completely depolarized, it must repolarize. So repolarization is a return to your baseline resting potential where we are negative inside and we will again become positive outside. So in this situation, your reference electrode and your positive electrode are still in the same place. So your exploring electrode is negative when compared to your reference electrode. Because it's negative, the graphical description of this electrical moment would go into the negative direction. You'd go below the isoelectric line. When repolarization is complete, the entire inside is negative, everything in the outside is positive, and once again, there is no difference between your reference and your exploring electrode, so you go back to baseline. It's back to 0. So that's kind of the fundamental principles of how we get the curves, the lines that show up on our EKG lead. So let's draw out what we normally see on an EKG. And it's going to be really important to keep in mind the electrical path through the heart. So if you've turned your pages in your notes, you see I've left a big space to kind of draw this out. I think it's helpful to add it in piece by piece. So let's draw it together. When we get into the full EKG lecture, past this introduction, we will talk about different leads that can be recorded. For right now, I am going to present what's called lead 2, and that will make more sense to you once we get further into the lecture. But lead 2, you have your reference electrode kind of up here and your exploring electrode down in this direction. So you're recording through the heart. This is kind of the direction of lead 2. This is like the best lead to look at for, oh, my arrow's kind of funny. This is the best lead to look at for kind of the norms of the heart, because it cuts through the heart in the same direction that the electrical current goes through. So it makes the most sense when you're first learning it to look at lead 2. And this will make more sense to you, the different leads, once we break that apart in the next lecture. Okay, so looking at lead 2, let's talk about what happens in the heart. The very first thing, if we're going to have an electrical moment in the heart, it has to be driven by the pacemaker. And the pacemaker is the SA node. So the SA node is here. So if we just add in the moment of the SA node, it has a spontaneous action potential, and that action potential travels through the atria via the internodal junctions. So SA node causes an atrial contraction. Now, it's important to remember that we are recording the electrical activity of the heart kind of way off on the skin. And it works to catch the electrical activity of the heart because tissue and fluids have ions. So electrical activity is conducted all the way up to the skin. But you do have to have a pretty big collection of cells all experiencing this action potential to get a deviation off of that line, to record a difference between your reference and your exploring electrode. So we're going to keep that in mind, that there does have to be kind of a bulk contraction to make a significant impact on our EKG lead. When we have the atria contract, you can see the cells of the atria would have been depolarized. So they would be more positive on the inside and negative on the outside. Whereas down in the ventricle, the depolarization hasn't reached that direction yet. So those are still in that resting state where it's more negative on the inside and positive on the outside. So I'm just going to draw this here because I can kind of feel it feeling lost. At this point, if we follow the leads, right up here by the atria is our reference, and down here distally is more our exploring. So if you compare the difference between these two, we have a positive deflection from the line, which is what we see every time there is a atrial contraction. You get a positive deflection off of the isoelectric line. We call that little positive bump, that recording of the electrical activity of the atria, we call that the P wave. What happens next? That wave of depolarization goes through the atria and it hits the AV node. The AV node is going to cause that slight delay from any change happening. And then once it gets through the AV node, it's going to fly through those Purkinje fibers. So if we draw this, let's add in what happens after. So we have a P wave. We have the electrical activity going through the atria. Then there's going to be a slight pause. And that pause or delay is the time when the action potential is slowed by the AV node. When it hits the Purkinje fibers, there's this kind of wave of electrical activity through the ventricle. And it typically causes a shape that looks like this. So if we first, again, label our P wave, then we can see the delay from the time when we're in the AV node. And then the deviations from the line that occur for the ventricular contraction, we label each of these 3 points. What can get tricky is that you don't always get all 3. So for that reason, they have kind of specific definitions for how they get labeled. This guy here is the Q wave. And the Q wave is the first negative spike after the P wave. So it is the first negative spike after the P wave. We call that the Q. The R is up here at top, the R wave. The R wave is the first positive spike after the P wave. First positive spike after the P wave. And then the very last one is this guy down here, and this is the S wave, which is the first negative spike after the R wave. First negative spike after the R wave. So if you don't have a Q, then if it just is flat and it has the first thing that happens is a positive deflection, you would still call that an R wave, because an R wave is the first positive spike after the P wave. The fact that they're not always present has to give us those really specific definitions. All right, so we have the P wave, which represents the atrial contraction. Then we have the QRS, which is the electrical activity of that ventricular contraction, the waves of electricity that fly to the ventricle. And the last thing that happens is the ventricles have to repolarize. So if we add this in, let's do it one last time, where we have a P wave. We have a slight delay for the time in the AV node. We have the QRS. And then a little while after, you will see, I'm trying to think what color I haven't used yet. Oh, what happened there? Little camera icon. You will see another positive deflection, and this is our T wave. If you are someone that looks at that and that is fine for you, that nothing about the T wave bothers you, you do not need to listen to the next 2 minutes of explanation. But for a lot of students, it really bothers them that the T wave is positive because it's this repolarization. So typically every year I have someone kind of saying, why is the T wave positive if it's a repolarization when we saw, this positive deflection for depolarization? So I'm going to give you the full explanation. This part of this explanation would never be on a test, but if it helps you to understand it, I want to make sure you understand. So I'm just going to draw the kind of wall of the ventricle like this. Here is the endocardium. Here is the epicardium. So when you are at rest, right, this is all positive on the outside, on both sides, the endocardium and the epicardium. Those cells are in their resting membrane potential. They're more negative in than out, so they appear positive. When depolarization happens, this is the part that should make sense, sound like what we've already learned. The endocardium depolarizes first. So it's negative here while it's still positive on the outside as that wave spreads, and that kind of gives us our positive deflection. Once the entire wall of the ventricle is depolarized, then you'd expect all the cells to be more negative on the outside than on the inside. But here's the tricky part. When it goes to repolarize, the epicardial cells repolarize before the endocardial cells. So for repolarization, I'm going to redraw that wall of the ventricle. The epicardial cells repolarize first. So they're positive here, while the endocardial cells are still depolarized. So from the vantage point or the viewpoint of the electrodes, the EKG sees this as a positive deflection because of the arrangement. Like if you look at these two, they actually look the same from the electrical standpoint. So if that helps, if that was something that was going to hold you up in your studying, that is the reason why a repolarization wave is positive, even though kind of what's happening in the cell is very different from depolarization. The other thing that can bother students sometimes is that we don't have a repolarization wave for the atria. And the reason we don't is that the repolarization of the atria occurs at the same time as the ventricular depolarization. And the ventricle is much larger, there's way more cells, so it is going to dominate the electrical activity that makes its way all the way up to an electrode, and you just don't even get to see the repolarization. It's buried in the QRS wave, and we just don't get to see it. So let's go to the textbook picture of this. So this is the same thing, much clearer than my drawing probably. This flat line that we kind of, our baseline line, is referred to as the isoelectric line. That is where the graphical depiction would be when your electrodes are recording 0, right? No deviation, no electrical moment. You can see that when the atria contracts, we get this positive deflection of the P wave, followed by the ventricular contraction of the QRS. And then a little while later, we repolarize the ventricle and we get our T wave. So on the bottom of your note page, you see some really important sections of the EKG that we should draw attention to. The first is the PR interval. The PR interval is the section on the EKG from the very start of the P wave to the very start of the Q wave. I know, it's called the PR interval and it goes to the Q wave. Technically, this should probably be called the PQ interval, but the Q wave is not on every lead. So because if the Q wave isn't there, you would kind of lose what this is called. That's why it's called the PR interval. So the Q wave is there, it goes to the beginning of the Q wave. If there is no Q wave, then the first deflection point would be the beginning of the R wave. So that's the PR interval. Your PR interval should be between 1.2 and, I'm sorry, I don't think I gave you the decimal in there. It should be between 0.12 and 0.2 seconds. This is the time it takes for the electrical potential to go from the SA node all the way through the atria and through the AV node, right? Because the beginning of the Q is when it finally gets through to the ventricle. So the PR interval is telling you kind of about the health of the transmission of the electrical signal through the atria and through the AV node. So if the PR interval is really short, if it's less than 0.12 to 0.2 seconds, that would suggest that there is some other path that's letting the electrical signal through to the ventricle. You kind of think of it like a second highway into the ventricle. It's not required to go through the AV node, because if it goes through the AV node, it's going to slow it down and create this interval. If the heart has any way to bypass the AV node, you'd expect a super short PR interval. If the PR interval is really long, If it's longer than this expected time, that would be what we refer to as a heart block. That there is something making it take longer for the electrical signal to get through the AV node. All right, that's the PR interval. The next one in your notes is the QRS. The QRS should be very narrow, like very squished together. The QR interval should be less than 0.1 seconds. That is because those Purkinje fibers have that super rapid conduction. It flies through the ventricle. If there is something that has changed the shape of the QRS or widened it and made it take longer, that would suggest that the electrical activity is not following those super highways of the Purkinje fibers. It's going through some other path to get through the ventricle. If it's flying through the Purkinje fibers, you should expect an extremely narrow QRS interval. The QT interval is the beginning of the Q wave all the way to the T wave. So you go all the way over, and this is your QT interval. The QT interval is like one full ventricular cycle. And sometimes people look at this for information about kind of the timing of ventricular relaxation. The last segment to look at is the ST segment. Right, so from the S to the beginning of the T. The ST segment is that plateau phase of the repolarization of the ventricle. Your ST segment should be flat or level with the isoelectric line. If the ST segment is either depressed or elevated, that's an abnormal finding. And we're going to go into more detail in the ischemia lecture about and actually in the later parts of the EKG lecture, about deviations to the ST segment. But that should probably sound familiar from pathophys when we talk about ST segment elevated myocardial infarction. This is actually what we're talking about. So our STEMIs cause an elevation of the ST segment. So I'm going to give you a little bit of notes on the EKG paper. This one is a little obligatory. You can't give an EKG lecture without kind of going through the details of the EKG paper. Although in our world, we most often are reading EKG on a monitor, so this kind of matters less in real-time PT stuff, but this is like great questioning for EKG questions for like board exams and stuff. So I have a picture of the EKG paper in your notes, and you can see the y-axis represents the change in voltage, whether it's positive or negative, and the x-axis is time. So the x-axis being time and the division of the paper can be really helpful when you're analyzing rhythm strips on EKG paper. So one big box is 0.2 seconds, and each big box has 5 small boxes within it, where each small box is 0.04 seconds. So when you're looking at a strip, it can be really easy to quickly see 1 second of recording, because if each big box is 0.2 seconds, then if you look at 5 of them in a row, you're looking at 1 second of time. So it's a very quick and easy way. And we were talking about these normal times for the PR interval and the QRS. And when you kind of can break that paper down into these segments of time visually, you can get that information super fast. For example, your PR interval should be somewhere between 3 small boxes and 5 small boxes, because the PR interval should be between 0.12 and 0.2 seconds. So it makes it, if you're looking at a monitor, you really truly cannot determine that, and the paper gives you the power there. The other thing that's really handy is the paper allows you to easily calculate heart rate without doing a whole lot of math. So there's a couple different methods to doing it. Since kind of 5 big boxes combined are 1 second, then you can look at a 6-second strip pretty easily. 1 second, 2 seconds, 3, 4, 5, 6. And each R wave represents the beat of the heart. So if you just count the number of R waves that are present in a 6-second strip, and you want to know how many beats per minute, and obviously there's 60 seconds in a minute, you just take the R waves you see in the R waves you see in a 6-second strip, and you multiply it by 10 to get to 60, and you have heart rate. So you can get heart rate in 6 seconds. Pretty handy. The other way is kind of a math shortcut, where if you look at where the starting with an R wave, how many boxes does it take until you get to your next R wave? If you get another R wave in one big box over, your heart rate is 300 beats per minute. If it's 2 boxes, so here we go, 1 box. If we go 2 boxes, then your heart rate is 150 beats per minute. If it's 3 boxes, it's 100. If it's 4, it's 75. So for people who work with EKG strips, these numbers become extremely valuable because it's very easy to have them memorized, and you can look at a strip and very, very instantly know a heart rate. So when we look at the presentation of the electrical activity, it's important to go through a few key steps. So we start here by saying, let's look at the P wave. Does it look normal? Is it in the positive direction? Is it upright? Do you have a P wave for every QRS? Because again, the P wave represents the kind of control the SA node has over the entire rhythm of the heart. So you would not expect to see a QRS without a P. The other thing you look at is, do all the P waves look alike? If you got a funky looking P wave, that is abnormal. Your EKG should be nearly identical, beat by beat by beat. You can go to the PR interval and look at the timing. We kind of already talked about whether it is too short. You have some kind of sneaker pathway into the ventricle that's bypassing the AV node. If it's too long, you have a block. Then you look at the QRS complexes. Do they all look alike? The Purkinje fibers are a set pattern. Every QRS should be identical. If they're not, it gives you information about how the electrical signal is spreading through the ventricle. Evaluate the QRS interval. Is it at a normal rate? Look at the T wave. Is it upright? Meaning, does it have a positive deflection? Does it look normal? Evaluate the RR interval. Is there the same space between every RR? That would be a normal heart rate. Look at the rate of the heart. Is it within the normal range of 60 to 100 beats per minute? And then always, always, always look at the patient and evaluate their symptoms. If you see something funky on the EKG, you look at your patient and what are they representing? How are they projecting? Are they having symptoms? Are they conscious? And that's always going to be an important step when evaluating what you see on a rhythm. Okay, so here are the rules that you can say, I have a patient who is a normal sinus rhythm. Normal sinus rhythm means that everything is running normally and that the heart is under the control of the sinoatrial node. That's where sinus rhythm comes from. So all these rules have to be met or you are not in normal sinus rhythm. You have regular P waves throughout the strip, and every P wave has a QRS. There's a 1-to-1. The PR interval is between 0.12 and 0.2 seconds, a normal time for that atrial spread through the AV node. The QRS interval is between 0.04 and 0.12. We We have a normal ventricular response. The rhythm is regular. Same number of boxes between. So I kind of draw this out to kind of go through the different rhythm disturbances. This is a regular rhythm, the same number of spaces between each beat. You can have a regular rhythm that is varying. So we see a pattern. There's a pattern here. It's abnormal, but it is regular. Every other beat, there's like a double. Or you can have a truly irregular beat where there's no rhyme or rhythm, there's no pattern, there's just kind of random heart rates going throughout. You can look at the atrial rate. How often are you seeing the P wave? And that should be between 6 and 100 beats per minute. The heart rate should be under control of the atrial rate. So these rules we're going to go back to again and again when we now go into the more kind of advanced looking at first how we truly get our leads recorded and then abnormalities to rhythm. Thank you guys for your attention, and I'll see you soon.